Year 13, Chapter 10, Integration, Lesson 5, Integration involving the natural logarithm function. So we keep coming back to this idea that integration can be thought of as the reverse of differentiation. Now, let's remind ourselves that if we start with the function ln of x and we differentiate this, we have seen that this results in 1 over x. Now, this tells us that if we integrate 1 over x, where x cannot be equal to 0, we get ln of x. So we can express this as follows. The integral of 1 over x with respect to x is equal to ln of mod x plus a constant. Now you'll notice that we're including this modulus here because of course ln of x only exists for x greater than 0. So for this result to be defined properly, we have to restrict this to positive values of x. So let's use our newfound knowledge to have a look at a few quick examples. We'll start with the integral of 5 over x dx. So as we've been seeing, we can pull out this multiplicative factor here of 5 outside the integral. So we have 5 multiplied by the integral of 1 over x dx. And then, of course, this gives us 5 ln mod x plus a constant. Now, let's have a look at a very similar example which somehow causes people far more problems. Let's look at the integral of 1 over 5x dx. Now, what people seem to often find difficult to understand is that this 5 here plays exactly the same role as the 5 in the previous example. It's just a factor, a multiplicative factor, but it's 1/5. So I could pull 1/5 out of the integral, and then I simply have a 5th multiplied by the integral of 1 over x with respect to x. So that gives me 1/5 ln mod x plus a constant. Now, I have seen people write down instead this as an answer. They see this and they say, wow, well, the answer must be ln mod 5x plus a constant. But that's not quite right, and ln mod 5x could be separated to give us ln 5 plus ln x using a logarithm rule. And then, of course, ln 5 is just a constant, which we can combine with this constant here to give us the answer, which is ln x plus a constant. So that's why we don't write down ln mod 5x as our answer. So let's generalise this. In general, if we have the integral of k over x dx, where k could be in the numerator or the denominator as a multiplicative constant, this will give us k multiplied by ln mod x plus c. So we're going to have a look at a few examples of integration, and we'll start by looking at some examples that will require integration by substitution to start with. So I'm going to integrate 1 over 2x plus 3, which is a reciprocal type function. And remember, at the back of our minds, we need to remind ourselves that the integral of 1 over x with respect to x is ln mod x plus a constant. And this function has a similar format to that. So what is our u function going to be? By now, you should have a good idea that this is going to be 2x plus 3, sort of an inner function, if you like, in the composite. The composite function here starts off with 2x plus 3, and then we take the reciprocal of that. So there's the two-step sort of process that's occurring, or the multi-step process. As we know, if we're doing the full form of integration by substitution, we differentiate. and then we do the sort of faux rearrangement, this sort of step we've been using just to simplify the question for ourselves and the process. So this then becomes the integral of 1 over u, and we need to be with respect to u as follows. I'm going to pull the factor of a half outside of the integral, as we've been doing in these questions for simplicity, so then end up with simply having to integrate 1 over u with respect to u. So I get a half ln mod u plus a constant, and then of course the final step is to replace u with 2x plus 3. So my final answer, half ln mod 2x plus 3 plus a constant. And that modulus function allowing us to ensure that when we take ln of something, it's always going to be ln of a positive value. Now, look at the original integral, 1 over 2x plus 3 with respect to x. Look at the final answer, and you will notice the connection. Can you start to think about how you might have performed this integral by inspection? We know that functions which are of the form 1 over will integrate to ln functions, and then think about where this factor of a half would have come from, and again refer back to the original question. Let's try out another example using the full format of integration by substitution before we start to look at how some of these examples could be done by inspection. 1 over 8 minus 3x is being integrated with respect to x. So the inner function in this composite is 8 minus 3x. du by dx is equal to negative 3. And then let's rearrange, or our faux rearrangement, so we get this result here. Now, our integral then becomes 1 over u, and I then have this as well. So let me pull out this factor of negative a third to simplify the process. By pulling out these multiplicative constants, this removes a lot of the confusion around some of these integrals, makes them much more clear, and results in fewer mistakes when you're performing the integral, because you're integrating a much simpler function and you're not worrying about the multiplicative constants. So this then gives me minus a third ln mod u plus our constant of integration, and of course final step, let's replace u with 8 minus 3x, so negative a third ln mod 8 minus 3x plus the constant of integration. So again, always think back to the original question, the integral of 1 over 8 minus 3x, look at the result, and think about how this could have been done by inspection. We can see that we start with a function that's of the format 1 over 8 minus 3x, so that's why we end up with the result ln of mod 8 minus 3x. But of course, we also have this factor of negative a third, which means we're dividing by the derivative of the inner function, and the derivative of the inner function is negative 3. So it's the same process that we've seen previously being applied again. Let's have a look at an example and see if we can do this by inspection. So we have the integral of 5 over 3x plus 1 with respect to x. Let's make sure the 5 is pulled out of the integral like that for simplicity. So 1 over 3x plus 1 being integrated. So 5 will be part of the answer. We know the answer will involve ln of mod 3x plus 1, but we also need to make sure we divide by the derivative of this inner function, which is 3. So 5/3 ln mod 3x plus 1 plus a constant. And that's been done very simply by inspection. Essentially, we're applying integration by substitution, but because the function is so simple, we can do it by inspection. Now, this relies, as we've seen previously, on this inner function here being linear. So this has got to be linear for us to be able to do this. So can we generalise this? Yes, we absolutely can. So let's suppose we have the integral of k over ax plus b integrated with respect to x. We know it's a reciprocal type function. The k is simply a multiplicative constant which will appear in the answer, but we know we're going to get the ln of ax plus b. We know we're going to need to divide by the derivative of this inner function here, so we'll divide by a, and of course there will be a plus constant of integration at the end. Now we can prove this result very simply by using the full process of integration by substitution. Let's allow u to equal ax plus b, then du by dx is equal to a, and using our sort of fake rearrangement approach here for simplicity, we get this. So our integral becomes the integral, k can come on the outside, the integral of 1 over u, and then of course we have du over a here. I'm going to pull a outside of the integral as well for simplicity. So we're simply left with the integral of 1 over u with respect to u, and we know that this is going to give us ln mod u plus a constant of integration. And then the last step, as always, is to replace u with what it is in terms of x. So we get k over a ln mod ax plus b plus a constant. And you can see that's the same result as by inspection. So the important thing to remember if you're going to apply this approach and use inspection to carry out your integral is, of course, that this function here must be linear. So the expression that's in the denominator has got to be linear for this to actually work. So let's look at another example, this time a definite integral that involves using limits. Now, we are going to do this in two ways. So we can explore the question two slightly different ways. The first way that I'm going to do this is by inspection, which means everything stays in the same variable x, and I don't need to change the limits, I don't need to do anything at all because I'm working in the variable x. So we know that these reciprocal functions integrate to an ln format, so it's going to be ln of 2x minus 1 modulus of, but I need to divide by the derivative of this inner function, so I need a factor of a half here. Now let's put in our limits here. There's no plus constant because this is a definite integral, and I can now use my constant, so I get a half ln of 2 times 3 take away 1 is 5, take away a half ln, and actually I will just put in the modulus sign here, a half ln of negative 3 modulus of as well. Now let's take a look at this. The first part is simply a half ln 5. 5 is a positive number, so the modulus of 5 is 5. But this part here, you can see that we need to actually use the modulus here so that negative 3 becomes positive 3, and so we have a half ln 3. Now this can be simplified quite nicely, so take out a factor of a half, ln 5 minus ln 3 in a bracket here, and then we can use our laws of logarithms to write this as a half ln of 5/3. So if we use the full integration by substitution, we then need to make sure we work very carefully with our limits in this. So I'm going to start by setting u equal to 2x minus 1. Du by dx is equal to 2. and this then gives me this sort of faux rearrangement that we keep seeing. Now I must make sure I change my limits because they're currently in terms of x and I want to work in terms of u. So at the moment these limits are in terms of x. So if x equals -1, this gives me u equals -3. Remember, I'm substituting into this result here. If x equals 3, this gives me u equals 5. So my integral now becomes the integral between -3 and 5 of 1 over u. And then, of course, we need this part here as well. Pull out the factor of a half, and then we just have the integral of 1 over u between -3 and 5. And we then get a half ln mod u between 5 and -3, our limits, -3 and 5, lower limit, upper limit. So again, we now don't need to convert anything back to x because we've changed our limits to be in terms of u, we just need to substitute them in. So this then gives me a half ln 5 minus ln 3. Again, I'm activating the modulus here so that I don't actually have ln of -3. The modulus then allows me to have ln of 3. And of course, you can see we then end up with the same answers that we had here. So both processes are equally valid. Using inspection can make work a lot quicker in certain instances, but you can also use the full integration by substitution method. You just need to make sure you understand what you're doing, how you're doing it, and make sure you don't make any silly mistakes. If you're using inspection, the whole question is done in terms of x. You don't need to change the limits. If you're using the substitution, you do then need to change the limits so that they are also in terms of u. Now, I'm just going to, for a moment, talk about the plus constant. And this is something that will become very useful when you do some work on differential equations in a later chapter. So we've seen that if we integrate 1 over x with respect to x, we get ln of mod x plus a constant. Now, there's nothing particularly special about this constant, and what I'm going to do is I'm going to rewrite the constant as the ln of a value. So I'm going to rewrite my constant as, let's say, ln of k. And that's absolutely fine, because we've seen that the ln function, the graph, allows any possible y value. So every number can be written as ln of some other number. Now, because I then have a sum of two separate ln functions, I can then use my laws of logarithms, which tell me that ln of a plus ln of b is the same as ln of ab. So I can then express this as the ln of mod kx. And I've incorporated my constant of integration into the overall ln function. And this is a technique you will need to use later on, particularly, as I said, when you're solving differential equations, something you will come across much later in the Year 2 course. So do bear this strategy in mind. So we're going to have a look at a few further examples which involve integration resulting in ln functions within the answer, and in both cases the questions will involve integration by substitution as well. So let's take a look at the first one. We're going to integrate x over 1 plus x squared. So it's not a simple question that we can easily do with inspection. I'm going to set u equal to 1 plus x squared. Now, can you see, as soon as I differentiate this, the derivative contains x. And we've also seen there's another x in the overall integral. So this is going to be one of those questions where one part of the integral differentiates to another part, and so a nice cancellation will occur. So, next step, ready for our integration. We get the integral of x, and remember I'm going to leave this x just as x for the moment, over u, and then in place of dx, du over 2x. Now, cancel, cancel, as we knew this would happen, and let's pull out the factor of a half, we then have a half the integral of 1 over u du. So that is a half ln mod u plus c. Now, the last step is, as always, replacing this with what it is in terms of x. So we have a final answer that's in terms of x, not in terms of u. But notice how I'm going to write it out. I no longer use the modulus sign here. Now, can you think about why I'm allowed to do that? And it's because 1 plus x squared is always going to be greater than 0. In fact, it's always going to be greater than 1. So this means that I don't need to worry about the modulus, because ln of 1 plus x squared will always be defined, because 1 plus x squared will always be a positive number. Let's look at another example. The integral of x squared over 2 minus 3x cubed. Now again, you will notice that one part of this function, 2 minus x cubed, can be differentiated to produce a multiple of another part of the function, in this case the x squared term here. So always watch out for that. If you can see that in a question, then it tells you straight away that integration by substitution is going to work very nicely in the question. So this becomes the integral of, now as I've been doing previously, I'm going to leave this x squared here until the cancellation occurs. So we have the integral of x squared over u, and then negative du over 9x squared. So watch the cancellation take place. Now let's pull out of the integral a factor of minus 1/9. And again, we're left with this very simple integral of 1 over u du. So we get negative 1/9 ln mod u plus a constant. And let's replace u with 2 minus 3x cubed. Now this time I will keep the modulus symbol firmly where it is, because 2 minus 3x cubed could easily take a negative value. So we need the modulus in place. Now, earlier on in the integration lessons, we learnt how to integrate sine x and cos x. We also learnt how to integrate sec squared x, but we didn't learn at the time how to integrate tan x. However, we can now do this. So that's our aim, to learn how to integrate tan x with respect to x. Now, tan x can of course be expressed as sine x over cos x. And this is set up perfectly for us to use substitution, because if I allow u to equal cos x, then du by dx is negative sine x, which of course relates back to another part of the function. So this is set up very nicely for me to use integration by substitution. So here is this part of the process, which remember is just a simplification that makes the process work very easily for us. So I have the integral of, now sine x I'm going to leave in the numerator as sine x. My denominator, instead of cos x, I'm going to write u. And here I'm going to replace this with this. So what happens next? Well, as we can see, sine x vanishes. I can pull a factor of negative 1 effectively out of the integral. So I'm left with the integral of 1 over u with respect to u, which of course is going to give me negative ln mod u plus my constant of integration. Now, what do we know about u? It's the same as cos x. So I get negative ln mod cos x plus c, and this is my answer. However, I can use my laws of logarithms here, because we know that ln of x to the power of k is equal to k ln x. And I'm going to use that law here. So in front of the ln, we have a factor of -1, which I am going to make a power. So this becomes ln of mod cos x to the power of -1. Note, this is not arc cos x. It is not cos to the -1 x. It is not the inverse function. It is the reciprocal function here. So I'm going to quickly rewrite this as ln mod 1 over cos x plus a constant, which of course is ln mod sec x plus a constant. So please make sure that you are aware here that this is not arc cos x. It is 1 over cos x here. And the -1 here can be slightly misleading, but we're using a logarithm rule which is all about powers, so that factor of -1 becomes a power, an overall power of -1. So what do you need to know? You need to make sure you are aware that the integral of tan x with respect to x is equal to ln mod sec x plus your constant of integration. Now, something worth noting about the 3 examples that we've just done. In all 3 examples, one part of each of the functions being integrated differentiated to another part of the function being integrated, which was what allowed the integration by substitution to work very nicely. So all 3 examples have been of the form here. So the denominator is some function of x that differentiates to the numerator, and as a result we get ln mod f of x plus a constant. Now the denominator might differentiate to a multiple of the numerator, but that's absolutely fine. You then just have a multiplicative scale factor in the answer. The key thing here is to look out for examples where one part of the integral is a derivative of another part of the integral.